I guess there's no more students come, so we start now. Okay, good afternoon, everyone. Today we are going to talk about the EE5104 and EE6104 Ca1. Our target of the Ca1 is to design an adaptive controller for a continuous time system whose structure can be written as Ys over Us, the transfer function. There are some points we need to note that first is only the output of the plant is measurable, and the second is the B0, B1, A1, A2 are uncertain parameters, which means that we cannot know the exact value of them. It is only known to us that B0 is a negative number, and there is no root in the right half of the S-plane of the planet system. So based on this evaluations and assumptions, if we have a transfer function y over u written as this, and we can define p, which can be treated as a differential operator at this state, and then we can rewrite the transfer function as rp equals kp zpu. For a reference model, we can choose a first order model, which is defined as HMS. For a step reference input, the steady state offset of the model is 0, and the responding speed is decided by the choice of tau. The reason why we write the transfer function as a combination of monic polynomial is that we're going to define two functions, the Rm and the Km. They represent the pole polynomial and the zero polynomial of the transfer function HM as respectively. In time domain, it actually shows how we describe the reference model. So with the reference model defined, if we want to analyze a system that can track the reference model, we firstly analyze the non-adaptive system, which means that we already know the RP, ZP, and KP, the exact value of them. So we arbitrarily choose the stable monic polynomial T of the second order, which can be defined below here. T equals P squared plus T1P plus T2. And it is the pole polynomial of the filter and the non-minimal realization of the plan. That means the transfer function contains some comparable pole points and 0 points. Moreover, we can import monic polynomials E and F, which can be defined in this gray equation, TRM equals RPE plus F. Then consider the control law, and when with the terms defined below, the G bar and G1 bar and the KPK star, we can write our U as this form: U equals minus G1 over TU minus F bar over TY plus K star R. Actually the process is on the right half. Firstly, we already know that from this slide, we know the RPY equals KPZPU, and we multiply E at the same time. The ERPY equals EKPZPU, and we use the T to substitute this part of the RP, and we can get our RPY equals 1 over T EKPZPU plus FY, and then we can get this form, which is actually the exactly same of these orange equations. So we can get our control law from here. This one and this equation is really important to remember. Consider the control law. If we have U, we can adjust our system to track the reference model, and with these terms defined, we can get the G1, G2, F1, F2. This is because this is the RP, ZP, and KP are known to us, which means we exactly know the specific value of these polynomials. So we can know these parameters or coefficients. And then we have our controller U, and we can define the auxiliary signal omega U and omega Y. This is just an intermediate term, so you can just use any other letter to substitute it. If the original plant is known to us, then with the appropriately designed reference model and and the polynomial t, the seed bar star can be calculated precisely, which means that the controller gain can be calculated precisely. And the omega bar can be obtained from the non-minimal realization of the dp with u and y, which is down here. Seed bar star equals minus f2 minus f1 minus g2 minus g1 k star transpose. And this is actually the ideal gain, which means that we write our controller input u as this form, and then we can track the reference model perfectly. But however, in practical case, the original plan is unknown, which means that we cannot calculate our seed bar star precisely. So the value of seed bar star is unknown, and it is not a constant, but a time varying gain. And then we need to rewrite our equations below. And this equation is quite simple from here. Actually, sorry, here. Actually the same, but we just substitute u with seed bar transpose omega bar. This seed bar is a time varying gain, and we introduce a phi bar, which is actually measures the error or actually the difference between our real gain and the ideal gain. So we rewrite our RMY as this one, and the first, second, and third term of the polynomial is actually the KMR, which is the reference model we introduced before, the non-adaptive system. And the last term of this equation can be written as KP phi bar transpose omega bar. It's actually our dynamic error. It measures how much our system far away from this ideal system. So the objective of the adaptive controller is to design such an adaptive input, which is u here, that the error would converge to 0, which means that we want our error converge to 0, and we want our output of the system y converge to our reference output ym. Appropriately designed. In order to do that, we are going to use the non-minimal realization of the plan and the non-minimal realization of the reference model. The control signal is designed so that the non-minimal state of the plan would converge to the reference model. By replacing RP, ZP, and KP, we can write down our output, the system output y as below. Y equals T omega y. This one is quite important, and we should remember that. We can also written it in matrix format as this below. We got the same result here, but in matrix format here. For reference model, we introduce omega m, which is omega m dot equals am omega m plus bm r, and this ym can be written as cm transpose omega m. This is our reference model, and our system model is omega dot equals ap omega plus bpu, and y equals cp transpose omega. What we want is to let this y converge to ym and e1 converge to 0. We use the idea of state feedback adaptive control system design. We know that we can define Lyapunov equation as follows: that V equals E transpose P E plus phi bar transpose gamma inverse phi bar. And do notice that we need to define a Q, which is defined by this equation, and we mentioned this yesterday in C3. Is AM transpose P plus P AM equals minus Q, where Q is a positive definition matrix, and by the Lyapunov functions and the Lyapunov method, we can write our V dot here. This is actually the exactly same process in the lecture notes. We can get our V dot equals E transpose minus QE plus 2 times sine function of K star E1 phi bar transpose omega bar plus 2 phi bar transpose gamma inverse and phi bar dot. with the KY lemma, we can get that if we choose our sit bar dot equals minus sign k star gamma omega bar E1, we can get our V dot here. We can get our V dot as E transpose minus QE. This is because our phi bar dot, sorry, here our phi bar dot is only because the sit bar star is a constant, so our phi bar dot is actually equals the sit bar dot. So we use the sit bar dot here, substitute the equation here, then we can get our V dot equals E transpose minus QE. And we know that V is the V is positive definition, and the V dot is negative definition because this Q is positive definition. And so then we know that V is bounded and stable. Besides, the sit bar dot can guarantee the Y will converge to Ym. And we put this omega and sit bar here as a time varying gain. And then we have illustrated the theory all we need so far. You can follow this whole process to design our adaptive controller. So let me show the simulation and code now. So can you see my MATLAB now? Okay. Basically, what we do is that we firstly design the zeta and omega is actually from the requirements in the CA. We have a real system, but we have a zeta and omega, and then we design gamma. It can be treated as gamma is here, sorry, here. And we design our parameters of the system and the nominators and denominators of the functions, and then we construct our planet system. This TF here is the MATLAB command of construct a control system using a transfer function. If you do not know how to construct such a control system or what does this command mean, you can use simply type help TF in the command window, and you'll get all there. The instruction will tell you how to use this command in MATLAB to construct a control system. And then when we define our KP, DP, RP, and our TP here, TP is a second order polynomial. And this coefficient equals the parameter here. And then we define our RM for reference models, and we can get our E and F. This decom actually is a function of the deconvolution method in MATLAB. If you have problem with it, you can check the MathWorks website. It has a full instruction about how to use the deconvolution and convolution functions. And then we calculate our F bar, our G bar, our G1 is actually based on the polynomials we have defined before. And then we get our K star. Once we have our K star, we can write down our sit bar star here. It equals K star minus G1 minus G2 minus F bar minus F bar 2. Well, actually minus F bar 4 and minus F bar 3 equals minus F2 and minus F1 in the lecture notes. So we run the script here, we can show that the poles of the system tells us there is no poles on the right half of the S-plane, and means that the plane is a stable plane, and the sit bar star is the gain here. It's actually the specific number we can calculate. The ideal gain is a constant, and then we can build a Simulink mode here. If you do not familiar with the Simulink, you can just use this script to describe your system. The Simulink is just you can visualize it. I think it's much easier than the script. You can see there on the left half is the non-adaptive model. It's used actually the sit bar star to get our input. And on the right half of the simulating case, actually the adaptive planet is an adaptive system. We calculate the view dynamically, and we get our adaptive control input. So we run the simulation here. What we need to get is actually like this. You can see that the adaptive signal can track the reference model quite good in general. Yes. And non-adaptive output, because it's an ideal gain we calculated, so it can track the reference model very well. And you're also required to discuss that you can see the blue one represent the adaptive gain. It is not a constant, and it is not actually exactly equals the ideal gain, which is represented by the green line. So this is what you need to discuss, and you need to do some experiments and write down your observations in the report. And then if we change our Q here, we change it like 0.1, then the gamma here will be 1, 1, 4, 1, 4, 1, 4, 1, and then we rerun our system. Let me see this adaptive control result will be not satisfied because they're fluctuating always. This is because our gamma is too small. So find an specific or appropriate gamma is also a part of the report, to design. Beside of that, you can also, let me first revert it to 100. You can also change the plan here, which means that the initialization of the plan is far from our reference model. Like I just simply change two numbers here, the transfer function coefficient. I just times 3 and times 0.1. And let me, sorry. Okay, let me rewrite here. We can see that though I changed the initialization of my plan, the general actually the tendency of the adaptive plan can track the reference model, but there are more fluctuation here, and this is what you'll need to discuss. And the non-adaptive model will refer like this one, like ion wave here. So this is because the initialization of the planet is not exactly the same as reference model. So basically, these are the parts what you need to discuss in the report. And I think that's all of the C1 here. Do you have any questions? Let me first share the sorry, let me first share the PowerPoint here. Do you have any questions about the CA whole process? And just type in the chat window or unmute your microphone. Or also you can type or ask any questions about C3 we talked about yesterday. So basically, what we do in C is C1 is you need to design an adaptive controller and discuss what kind of parameter change can influence the system, can influence the tracking result. You choose different TP, you choose different gamma, you choose different initialization of the band. You see what the observations, and you can discuss or make your conclusion about why it caused such a result. Okay, I think there is no questions here. If you still have questions, you feel that you are not understand the CA after these sessions, you can just email us or just come to our lab. Okay. Thank you. I think today we finished it here. Thank you.